Hello guys, in the previous lesson we have created the A hat and B hat dynamics, and so we have derived some properties on the estimation of the A hat and B hat with the way of the improving our results. And so we have designed the sum controller rule based on the feedback linearization rule. On the linear or non-linear system, you can use the anywhere, which is applying on the Lyapunov stability theory. And so, in this lesson, we will design the controller with the specific reference values. Okay? And so, this is the controller design block in here, like this one. And so, if I'm running this code, and then we will say that this U or input value is generated from some specific frequency range. But in this case, in the reference tracking problem, we should define the reference signal, like in the in the paper written. Okay, and so we should design the reference signal in here. Okay. And so, reference signal can be defined by the X ref is equal to the bias plus amplitude times sinusoidal signal Q or W times T. Okay? And so, this W is the angular frequency of these things, and 2 times pi times F should be included in here. And so, the F is equal to 0.1 frequency range or hertz. And also we need to drive the X ref dot, because in our controller approach we should use or utilize the X reference derivative term. Okay, and so if I take the derivative values of these things, and so we have the amplitude times omega times or W times cosinus omega times T. Okay. These are the reference signal. And so, how can we drive the controller input in here? Okay? And so, U should be assigned to the to the specific rules coming from the previous lesson. U must be equal to the X ref dot plus A hat times X. X is measured value plus K times E, K always be positive in here, and so we need to also define the error term in here with the definition of the error is equal to the X ref minus X measured. Okay, and so we need to divide the whole terms with the B hat value, and so this must be stabilized are the system which utilize to the A hat or estimated A and B values. Okay. And so U must be defined in here like this one. The B hat should be given at this moment, and so X ref dot should be given, and so A hat is also given in here, and X plus K times error signal. Okay. And so the error term should be defined in here. Error must be equal to the X ref minus X. Okay. And also we need to input this controller design or FAT by the A hat and B hat value. Okay. And so we should add the X, A hat and B hat here. Okay. And so the X coming from where? To these things, because we can measure this X value by using some sensors or transducers or something like that. Okay. And also we need to fed the A and B value, but this A and B value is the sonnet or the real A and B value, but in our controller approach or in the microprocessor, we should only utilize to what the estimator models A or B, and so this can be given at this moment. But in order to simplify all the things, A hat out and B hat out should also be defined at this moment. Okay, A hat out is equal to the what? A hat, and B hat out is also B hat. Okay, and so we have this kind of information in here, and so we can define the new things in here like this one. A hat and B hat should be fed into the what? This term. Okay, B hat is also given at this moment. So we need to also give the positive k value in here for the coefficients. Okay, k is equal to what? The 10 in here, like this one. And also we need to give the x ref out value in order to compare the R results. Okay, and so the reference results can be given in here. This is the estimation error, but we can use goto in here like this one. This should be equal to the x, and this should be the what? The xref. And so we can compare the whole results in here like this one. Okay, we have a max value in here, and so we need to give the some scope in here. Okay, and then if I run this code, okay, bias is not included in here, bias value is 5 and amplitude value is 2. Okay, it's an arbitrary numbers, you may choose anything in here. Okay, and so if I run this code, xref out, okay, xref out should be assigned at this moment, and xref should be assigned. Okay, and so if I run this code, the algebraic loop error is given at this time because the A hat and B hat value is not generated at this model right now. Okay, and so how can we solve this problem? We can use the unit delay in here. Okay, but this may be not equal to the standard solution because we should assign the initial conditions like this one. And so if I run this code, the xref is properly control or track the reference signal. Okay, and also we match the whole values in here. 1.1 is stabilized in here like this one, and B is also stabilized like this one. Okay, and so these are the first solution in here, but if we assign the k is equal to the 1000 in here, and so xref cannot be control of these things because A hat is not equal to this region. Okay, this is an arbitrary number, and so we should not give the higher values at the k in here because the learning rate is slower than this k, and so this system cannot be controlled the R algorithms. Okay, and firstly we need to recorrect the whole the terms in here like this one. The A hat and B hat should not be used in here like this one, and so the A hat is now if the fed with this integrator value like this one, and so the second term is equal to the A hat, the third term is equal to the B hat in here because A hat and B hat 2 and 3 terms in here. And so if I run this code again, and then xref is now also not control these things because the k is always greater than the learning rate. And so if I run this code with the 10 coefficients, and so the coefficients properly track the reference signal. Okay, and also we can show that the 1.1 is regional stable and 1.1 is regionally stable in here. And so what about the AM -1 and 100 in here? If you are lower values of the stabilizing term and learning rates, if we run this code, and so the controller is perfectly run at this moment, and A hat is a oscillation term at this right now, and then the A is also given at the right hand position. But 1.1 is given like this one, 0.9, and 0.9 is also be used at this time. Okay, and so the X hat is also track the reference signal in here, but B hat and A hat is also stabilized. Okay, and so if I run this code the 100 times in here like this one, the reference signal is always okay, and so the A hat value is a sinusoidal signal in here, and B hat value is sinusoidal signal. Okay, and so what happens if we change the rules of the the A and B value in here? Firstly, we should remember that the A hat and B hat value is given at this moment. Okay, and so what happens if we change the B is equal to the 10, A is equal to the 5, and if I run this code with the initial value of the 1 and 1, and xref is also driven to the reference signal, there's no problem in here. Okay, but in B hat or B hat stabilize the whole region in here in the 5.8, or A is equal to the 3. And so what happens if we set the 5,000s, or no, I'm sorry, 500 at A and B is 20. Okay, and so if I run this code, and then the xref and bref value is unstable in here. Okay, because the AM stabilization term is too small right now, and so if I'm increasing the AM in here like this one, the xref value should also be slower. Okay, and also we should given to this system with the high rate of gamma value in here like this one, and so the system cannot be approach these things. And so what's the problem of this thing right now? Firstly, we should understand that if we have the 1 and 1 value in here like this one, should be changed with the 320. Okay, and so if I change this code like this one, and then you see that our algorithms is okay. And so if I had the high learning rate and high stabilization term and in the estimation model, we cannot reach the solution, because if we don't have a initial condition in the A hat and B hat value in a proper way, and then we cannot reach the solution. You should remember that. And so always you should put the equilibrium points of the A and B value. This is not the exact, but the equilibrium points always goes to the stable region. Okay? And so this is how we can implement the controller design on the linear system theory, or linear system state space. And so the estimator model should be okay with the feedback normalization controller in here. In the next lesson we will drive the estimation model for the non-linear systems, especially in the scalar form, because we need to define also a Lyapunov function in both cases for the estimator model and controller design. You should remember that, or notice that the whole controller design and estimation model are separate things right now. But if we combine the estimation model and the controller design in one Lyapunov energy function, we will call it the adaptive controller perspective. Okay? And so in the next lesson we will transform the R system to the nonlinear one, and then we will estimate and control it with the same analogy.